Spooky action at a distance. An in-depth explanation. Spooky action at a distance is a term famously coined by Albert Einstein to describe one of the most perplexing and counterintuitive aspects of quantum mechanics, quantum entanglement. This phenomenon has intrigued and puzzled scientists for decades, as it defies the classical understanding of the universe and raises fundamental questions about the nature of reality. The basics of quantum entanglement. Quantum entanglement occurs when two or more particles become linked in such a way that their quantum states are interdependent, regardless of the distance separating them. This means that any measurement of one entangled particle instantaneously affects the state of the other, no matter how far apart they are. This instantaneous connection between entangled particles seems to violate the principle of locality, which states that an object is only directly influenced by its immediate surroundings. Einstein's skepticism and the EPR paradox. Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, formulated the EPR paradox in 1935 to challenge the completeness of quantum mechanics. They argued that if quantum mechanics were correct, it would imply spooky action at a distance, which seemed impossible within the framework of classical physics. The EPR paradox suggested that there must be hidden variables that quantum mechanics did not account for, which would preserve the principles of locality and realism. Bell's theorem, an experimental confirmation. John Bell, a physicist, developed a theoretical framework known as Bell's theorem in 1964. Bell's theorem provided a way to test the predictions of quantum mechanics against those of hidden variable theories. Bell's inequality, a key aspect of his theorem, set the stage for experiments to determine whether quantum entanglement truly exhibited non-local behavior. In the years that followed, numerous experiments were conducted to test Bell's inequality. These experiments, most notably those by Alling Aspect in the 1980s, consistently showed that the results supported the predictions of quantum mechanics and violated Bell's inequality. This provided strong evidence that quantum entanglement does indeed involve spooky action at a distance. The nature of entangled particles. Particles become entangled. Their quantum states are described by a single wave function that encompasses the entire system. This wave function represents the probabilities of the possible outcomes of measurements on the entangled particles. The entangled state persists until a measurement is made on one of the particles, at which point the wave function collapses, and the states of both particles are determined instantaneously. Applications of quantum entanglement. Quantum entanglement is not just a theoretical curiosity. It has practical applications in various fields of science and technology. Quantum computing. Entangled particles, known as qubits, form the foundation of quantum computers. Unlike classical bits, which can be either 0 or 1, qubits can exist in superpositions of states, allowing quantum computers to perform complex calculations at unprecedented speeds. Quantum communication. Quantum entanglement enables the development of ultra-secure communication channels. Quantum key distribution uses entangled particles to create encryption keys that are virtually impossible to intercept without detection. Quantum teleportation. This process involves transferring the quantum state of a particle to another particle at a distant location using entanglement. While it does not involve the physical transfer of matter, it has potential implications for future communication and information transfer technologies. Challenges and open questions. Despite the experimental confirmation of quantum entanglement, many questions remain about its implications and underlying mechanisms. One of the most significant challenges is reconciling quantum mechanics with general relativity, as the two theories describe the universe at different scales and appear to be fundamentally incompatible. Another open question is the nature of the collapse of the wave function. While quantum mechanics provides a mathematical framework for predicting outcomes, it does not explain the process by which a superposition of states becomes a single definite state upon measurement. Conclusion. Spooky action at a distance remains one of the most fascinating and mysterious phenomena in quantum mechanics. It challenges our classical notions of locality and reality, forcing us to rethink our understanding of the universe. As research in quantum mechanics continues to advance, we may uncover deeper insights into the nature of entanglement and its implications for both fundamental physics and practical applications. The study of quantum entanglement not only expands our knowledge of the universe, but also inspires awe and wonder at the strange and beautiful nature of the quantum world.